my talk is about kind of NLP a little bit, but kind of more around Gensim and kind of what it offers as a package for doing natural language processing and kind of some of the models it exposes, some of the kind of text processing you can do with it. I found it to be not super either well known or used quite as much as kind of other tools out there in the Python ecosystem. NLTK is obviously used a lot and really well known. And I'll talk a little bit about how NLTK can kind of augment Gensim, because Gensim tries to be kind of a smaller package in terms of what it can do. It's really focused on a couple things, which I think is really good. Doesn't try to do too much. So kind of just talk about Gensim, how I've used it in the past, how you can all use it for either the kind of text analytics side of it or potentially kind of the querying side of natural language processing if you want to kind of build a pseudo search engine or do similarity matches for however you kind of want to define your documents. And I'll talk about a couple alternative definitions of documents that you can potentially use in other aspects. So the kind of the rough outline for this talk, want to give kind of a quick introduction to NLP, super quick, 5 minutes. Not gonna teach you the low-level details here, but just enough so when I start using terms later, you may have heard it. And then kind of want to talk a little bit about Gensim, at least the background of it, where you can find more resources on how to use it in the future. I promise it's being actively developed. I hate when someone's like, "Oh, this is a great package. You should use it," and it hasn't been developed in over a year. Talk a little bit about some of the mechanics of Gensim and kind of the workflow that I've used. Hopefully, if you're kind of going off and like, "Oh, I have this awesome corpus that I want to analyze," hopefully this will kind of give you the workflow of, "Oh, I have these documents. How do I do some transformations on them and potentially model the outcomes?" Then I'm going to talk about a couple kind of use cases, examples. So I'll talk about my background here in a sec, but I've worked on kind of building recommendation systems in a prior job where we were able to kind of translate using natural language focused models into more recommendation tools. So I'll kind of talk about that. And then kind of talk a little bit more about a purely kind of analysis example where I looked at some inaugural address from the presidents all the way back till 1789 to the one in 2009, and just kind of not going to talk about like the findings of them, just kind of want to talk about like the workflow and how I went from, I have these documents to, now I have some analysis that might be interesting to share. So this is me. I just kind of guessed on the arrow. Just kidding. You got to figure it out. So this is me. This is when I was younger and better looking. That's my Twitter and write a blog, though I haven't updated in a long time. My kind of educational background is more focused on kind of accounting and mathematical finance. If you were at the swarm optimization one, you know that accountants are potentially the most annoying breed of person, and that's me. I kind of transitioned more into kind of media analysis, but then after that I worked at Zulily, which is a Seattle company, kind of working on their data science team, doing kind of operational analysis and recommendation systems, things like that. And then I've since left there. I run kind of a one-man kind of freelance consulting group where I focus more on kind of what I kind of historically care about, kind of algorithmic trading, financial tech, things like that. So NLP is useful in kind of all those aspects, and I found Gensim to be kind of a great kind of prototyping language or even a production language. You can use it. I mean, certainly there are tools out there now like PySpark, which has LDA, I believe, and has Word2Vec, which might be more amenable if you have massive data. But some of the things I'll talk about with Gensim make it usable for large amounts of data, even if you're only using one machine. That kind of one of the core tenets of Gensim is this kind of streaming idea where you use variational bayes or other kind of update procedures in the algorithm, so you don't have to store it all in memory. So I'll talk a little bit about that. But kind of first as an introduction, to NLP, and you can't do NLP in 5 minutes. It's like you're not wrong. You're just and this is PG-13, so. So I kind of think of NLP as and kind of text analytics as kind of two broad spectrums. You kind of have this front side, and it's not really that different from your kind of generic machine learning that you might be doing. You have this kind of like text encoding where you have a data set and you need to encode it, maybe do some dimensionality reduction, something like that, so you can actually have something worth analyzing. And then there's the kind of the modeling aspects of it where you might use LDA or Word-to-Vec, and I'll talk a little bit about those to try to kind of derive meaning or derive some sort of something you can fit in your head about these million documents and some kind of representation thereof. So the first kind of part of all modeling, natural language or otherwise, is you have this raw data and you need to turn it into vectors. You basically need to turn it into numbers. So here we have kind of two examples. This is a document. This is not a document. I almost put this is not a pipe. I'm a fan of the French stuff, I guess. So this is kind of the most classic, or I guess it's not really the most classic, but this is kind of the most common used text encoding representation you can have. It's called the vector space model. There's another one a little bit more classically used called the Boolean, standard Boolean model, but the vector space model is used quite a bit more. And so you've actually seen this encoding. I'm sure you have. If you use R and you have a text variable and you need to encode it where you have, say you have 3 different options in a categorical variable and you need to encode it, you'll then basically expand it out where you have 3 columns and you'll have, say you have a color is a feature of your model and it could be red, green, or blue. You'll have a column for red, a column for green, and a column for blue, and then an indicator variable in that. This is really not too dissimilar from that at all. So you've seen this before. You just haven't. If you're not familiar with NLP, you might not have seen it where the entire data set is a categorical variable. So what you end up having with this vector space model is basically every individual term. That's the dimensionality. So you can kind of think if I have 20 terms in my entire corpus, that's going to be the dimensionality of the vectors in this kind of vector space model. So this is kind of the base representation. After that, there's a lot of kind of encodings you can do on top of that. One of the kind of more common ones you'll see is what's called TFIDF. It's term frequency inverse document frequency, which tries to reweight the vectors based on how often or how infrequently they occur in the underlying text. This can be really good. For instance, you see here, how we have this is a document. Because of the ubiquity of this is a document, they're really kind of meaningless if you were to kind of find some information because they're present in the entire text. So you'll want to use this kind of inverse document frequency, which happens to be modeled in Gensim, where it can kind of go through your corpus for you and reweight these things. So the point of these last 3 slides is really, we have this document, or we have these documents, and we need to turn them into vectors. So once you get there, you kind of have this kind of underlying problem where you have this massive dimensionality problem, right? If you have 1 million words in your corpus, you then have 1 million, your space that you're working in is of size 1 million. So you have a real kind of problem of finding anything interesting. This is why you typically see cosine similarity used a lot more than Euclidean distance in NLP tools because they work a little bit better under these high dimensional spaces. That said, there are kind of 2 broad models and transformations that I would kind of classify when doing NLP. You have these kind of decompositions, which is you take this vector representation and you project it down into a lower dimensional space. These are kind of, if you've seen PCA, it's a very kind of similar idea, and certainly there's these 2 topics get kind of meshed in together because you can have probabilistic PCA or things like that. So it gets kind of they get kind of muddled together. However, I guess I would kind of, if I were to categorize them in my brain, this is kind of how I would think about them. both outcomes are really useful. These decompositions are maybe a little bit better for querying. I have these two documents, and here's their representation after PCA, and I want to find the similar documents. Whereas probabilistic models are a little bit more interpretable. You can say, this document was kind of arised due to its probability of whatever topic at hand. So two kind of examples for that. So one example, and I'm going to talk a little bit later in the inaugural address example, is LDA. So LDA is kind of a workhorse when it comes to natural language processing. The kind of basic idea is you have words, topics, and documents. Documents arise are kind of composed of some probability of the individual topics. So if you imagine, like I'm writing a document, I'm going to select, I'm going to roll a dice, select a topic. When I select that topic, I'm then going to select a word from that topic based on the probability of the word given the topic, and then write that down. And so that's kind of the generative model of LDA. So you can actually do like really kind of nice and useful things. This is from this is now from the data lab at UW around, but it's just kind of a visualization. There's lots of tools out there in R and in Python for visualizing the outcomes of LDA. But what this kind of shows is, so you have these words over here, and you have the topics kind of up top, and you have, what's the kind of probability or the relative probability that the word was generated from that topic. You can kind of slant this around a little bit. If you kind of think, if a document is a collection of words, one slant you might make is, what if a person is a collection of actions, right? So you might have some person who's shopping on a website if you work at an online retailer or something like that, and then the document or the words that they are then showing might be the actions they're taking on the site. So you have these kind of choices within a person, and then you can potentially try to kind of create personas are really popular nowadays in online marketing. So you can kind of potentially create these personas from the individuals that are saying, this kind of group of people is really likely to have been generated from this topic. So that I would classify as more kind of a probabilistic approach. Another one is Word2Vec, which is getting a lot of popularity. I found Word2Vec extremely useful for kind of querying similarity searches and things like that. I have found it of dubious interpretation though, of like, what does this actually mean? It's quite often you'll have these massive vectors, and it's not super clear how to use them beyond what their cosine similarity is or something along those lines. That said, if you do want to visualize these things, something like PCA on top of Word2Vec or TSNE is another really good choice of kind of decomposing these vectors so you can get some visualization. There are two kind of broad topics, or broad kind of classes of Word2Vec, which is like kind of a continuous bag of words, which you're using the kind of surrounding text, surrounding words to predict the word, or where you have kind of the skipgram model where you have the word in general and you're trying to predict kind of the words around it. And that kind of classification process is what produces the vectors you end up using. So that was kind of roughly the 5-minute introduction to NLP. So now a little bit more focus on Gensim. So there are a lot of tools out there that you might think of before you think of Gensim. There's scikit-learn, which is amazing, ValPowerRabbit, Spark, Mallet, tons of these things, and they're all really good. There's no doubt about that. However, they all have maybe disadvantages for kind of quickly integrating, an NLP model or something you want to do analytically with the data you actually have. Scikit-learn is great, but its text analytics features are maybe a little bit limited, and that's not by the lack of the developer's ability. It's more probably not of super focus to them. You have ValPowerRabbit, which I think is at least sponsored by the good folks here at Microsoft. Spark, which is getting really popular, and Mallet, which is kind of it's been around and well tested and whatnot. The problem with all these is they require like quite a bit of setup. So like if I wanted to use valpyrabbit or mallet from Python, quite often you have to like shell out to another command or use it in these kind of like nastier workflows, whereas Gensim is kind of pure Python. You can just import it in. I have some examples later that show that. So it makes it quite a bit easier. And that's kind of what I mean by low friction is you can have your regular Python code and you can just kind of bring Gensim into it. If you're doing some text processing or something like that, it's not a big step to next, integrate Gensim. Whereas, if you wanted to use, mallet or something like that, it really kind of takes some additional overhead to think about that. Whereas really, you probably want to focus more of your brain power on the problem at hand. So this is Gensim. Like all great Python packages, it's X for humans. I was kind of interested in it. Being a human, I thought I thought it could be useful. So if you want to learn more about it, that's it. That's where you can go. The tutorials are awesome. If you really want to start using Gensim, just follow those tutorials. They're great. Some particulars about Gensim. Here's its homepage, GitHub. One thing to notice is it's LGPL licensed, not your kind of typical MIT or Apache. So if you do think about kind of using this as part of your system, really think about the ramifications of what that license means and what you're trying to do. Be a good citizen. We're all professionals, so be a professional. So there's some kind of like next level things going on in Gensim which are not necessarily reflected in the documentation yet. So there's some kind of automatic like text summarization, which is getting pretty interesting. There's some kind of extensions to WordDevec, DocDevec, which is kind of interesting. Talk a little bit about why you might be interested in DocDevec as opposed to WordDevec, depending on your applications. And then kind of classification is becoming kind of interesting and a little bit more usable with WordDevec. You can actually kind of produce these likelihood scores and then use the likelihood scores to make classification calls. So that's kind of the background of Gensim. So I want to talk a little bit more about like kind of how you actually use it. Right, so there's these kind of like workflows or these kind of objects that exist within Gensim, and how you use them is kind of the focus of this next few slides. So here are kind of the features of Gensim, or at least kind of what it says they are. And so I kind of want to break some of these down and talk a little about kind of like their use and why they're nice. So we have memory independence, which is great when you have tons of text and you have a little bitty computer. The interfaces are really nice, and I'll show them. This is my favorite part about Gensim is it's just so fast to go from I have a document to now I have vectors, and now I have a model that I can use for kind of further analysis or recommendations or whatever your kind of particular use case is. And then there's these various models, which I'll show kind of two examples of. So this memory independence is really important. Gensim is designed, with the idea that if you're doing text analysis on millions and millions of documents, there's no way you're going to be able to fit it into memory. So its main point is around memory independence, both from an algorithmic perspective and the kind of learning that it does, and the algorithms it chooses to do that learning. And then there's operationally the idea around streaming in text and basically reading lines off disk as opposed to reading everything off disk into memory and then moving those documents through the model. So I talk about memory independence. I'm not so sure where DevEc actually is memory independent. I believe it grows linearly with the corpus size. LDA I know for sure is via Hoffman 2010, which is a really good paper. I would recommend checking out. And then operationally, there's this kind of side which I just talked about, and it comes down to pretty simple stuff. So here's an example. There's this smart open package written by the same person who writes Gensim. You could do this in pure Python really simply too. We're just reading lines off disk, not really holding the entire corpus, and then sending them through. So that's kind of something to be cognizant of. Don't read everything to a list and then pass it in. I've trained LDA on Gensim with millions and millions of documents, and it's really not a problem as long as you adhere to these couple things. So some of the interfaces then. So Gensim has a couple of objects that are specifically designed for dealing with text. So there's a dictionary, which is exactly kind of what it sounds like. It contains the underlying vocabulary of the corpus you're working with. So what this means is kind of basically an index where you have a mapping of IDs to tokens, and you have various kind of methods around that are useful, such as converting the text. So for instance, converting my doc into the kind of bag of words representation of that, or basically the vector space kind of representation thereof. The other side of this are kind of what you define yourself, which is the corpus. So the corpus typically looks exactly like this. It can get a little bit more complex, but the main focus here is you override the iter method, and then that's how you yield your documents out. So what you can see is here I have this docs, which is just, you have two documents. They're already separated into kind of a list of lists. Obviously, based on what I just said, if you have a massive amount of documents, don't do this, but for the purposes of an example. You can then pass in this set of documents to this dictionary. It will read through it and then ascribe an ID to a term. And then once you do that, you define this corpus, you override the iter method, you have your documents, and you just basically loop through them and yield out the bag of words representation. Which is kind of like this vector space model. The only thing that Gensim does is it tries to be a little bit smart around the sparsity issues that you'll have. So for instance, if you had 1 million words and you wanted to represent one exactly as and if you had my doc, you might only have two terms in there that are one, and you'd have 1 million minus 2 as zeros. So Gensim will be smart around that sparsity and not store zeros when it doesn't need to. So that's kind of the high level, I have my documents, now I have my dictionary, and now I have my corpus. The next step after that is kind of doing models and transformations, and Gensim kind of uses these two things somewhat interchangeably in the sense that, and I do too. Transformations, you have Word2Vec or LDA or something like that. You're kind of transforming this vector space representation into kind of a set of topic probabilities, or if you're using Doc2Vec or Word2Vec or LSI or something like that, these kind of lower dimensional representations. And so I like to kind of think of these. It's kind of nice. Scikit-learn kind of spoils everybody in the sense that the API is extremely standard across different machine learning algorithms you might do. They kind of all have this fit method. They all have this train method. They do a lot of the kind of the same things that's different and separated from from the model at hand. And Gensim is pretty similar there. Kind of fundamentally, you need to pass it a corpus. You'll pass it kind of a set of quarks which are model specific. So if you're doing LDA, you might have kind of the number of topics that you think or you want to kind of a priori select. Or for Word2Vec, you might kind of choose you might choose the size of the vector representation that you want. But kind of fundamentally, it all kind of looks the same. You'll just have a couple different letters up front. And then the next step of that is after you have the trained model, you then need to kind of access the vectors. And so what Gensim does is it uses the kind of this array notation to produce the transformations for any document. So if I was to then pass in my doc to this model, it would then, the output of this call would be the whatever the model produces, be it the topic probabilities, be it the vector associated with it. So a couple other just kind of mechanics. At some point you're going to train a model, and then you're going to need to save it or load it. So there's these kind of utilities for that. To give an example of a real world example of kind of saving and loading, one thing we would do at Zulily is we would train a model on kind of a really big beefy machine, save it, and then push it out to the various servers, so it could kind of be local to the actual API, whoever's making the API call to get the scores. So this kind of model I/O is not that interesting, but useful. And then there's, so in kind of NLP literature, there's these various kind of formats that are kind of quite often used. SVM Lite is not LDA specific, but it's used quite a bit to ignore sparsity issues, or at least get by them to some degree. David Blay for the Blay corpus is pretty well known. And then there's a low corpus. So there's very options of serializing and deserializing both your corpuses and your models. So I mentioned earlier that LDA, or excuse me, that Gensim is pretty like small in its scope. So this is probably the best you're going to get in terms of text cleaning. So be aware. And I like that though. I mean, I'm actually a fan of trying to do what you do really well, and outsourcing or getting other people to do the stuff that you don't do well. So this is where I say you probably need more, and this is where NLTK, and this is kind of what I was saying earlier, where I plug NLT for just a bit. So things like stop words, stemming, those kind of things, which are kind of the fit and finish of an NLP model, are contained better within NLTK, or are kind of more useful there, or more robust, at least the kind of features there. So just kind of be aware of that. So that's kind of the background. So I want to kind of go in a couple case studies and kind of just give you some examples of Gensim in real life. So it's demo time. Yeah, I didn't realize there would be a 12-foot tall wacky inflatable arm man above me. Okay, so this is an example that's really tiny. So Gensim happens to be extremely simple to kind of plug into other Python libraries. So I kind of wanted to show that. So here we have, God, that is just awesome. So here we have, I know there's a lot of code, and I'm going to break it down here in a second. But this is basically you kind of think of this, I wouldn't put this into production certainly, but as a very kind of like example of a really cheap, simple recommendation system that you can use Gensim for. So this uses Flask to kind of handle the HTTP requests, but then it uses this word devec to train. So what you can see is, I kind of did this for example, but as you can see, if I have these 3 products, I can then pass in kind of a term to say, give me the vector representation of that, and now I have a little API where somebody can, hit my API and say, you know what, I have this term, what is its vector representation? Or I have this product, what is its vector representation? Which, the vector in and of itself is maybe not so interesting. What is interesting then is when you have multiple products or multiple words and you want to know the similarity between them. So that's where you can do something like this. So say you had an individual who just made like one choice, product C, right? So I made a purchase and it happened to be product C. And maybe later on your page you have kind of an Amazon-esque you might also like, or you might also be interested in this. So what you might do there is say, if you're the website designer or you're kind of running the website, you want some way to fill that up. So you say, oh, this person chose product A. Let me then make a request to the server and find out what other products are similar to that kind of fundamental or that underlying product C or product A or what have you. So what this is doing, and I'll show how this works in a second, is it's basically running kind of a cosine similarity between the choice the customer made and the various other terms in our corpus, which here just happens to be product A and product B, and returning the similarity. Then you could do some ranking or something like that to then kind of produce your recommendations. So let's see. So we talked about the term weight. Kind of talked about the similar products. So there's the nasty code that you don't want to look at. So here's kind of here's the training part, or I guess maybe more the instantiation part. So we have these products. So So if you remember earlier when I showed like, okay, this is very similar to how the other models work, where I had model name and then random quarks. This is what you might actually see for a Word2Vec specific choice, where you have these kind of the input corpus. You have min count, which Word2Vec kind of says, as I'm scanning through this text, how big should my window be? And then the size is how big you kind of want your basically how big is the projection vector. And so that was 10. So if you noticed on the website we looked at just a second ago, the vector you saw was of length 10. So that's where that came from. So there's how to create the size. There's that window. Trimming is really useful. So like I talked about earlier, there's this kind of idea behind continuous training and being able to update and stream in additional documents to your model. But one thing you might realize is that as you train a really big model, the model itself becomes really big, not even the corpus itself. And this is why I referenced earlier Word2Vec maybe not being completely size independent with respect to the corpus. But one thing you can do is you can trim the underlying vectors, and what that means is it'll compute the L2 norms of the word vectors. However, that limits your ability to do additional training on top of that, because it basically clips your vectors off. So you can't train additionally, but it massively reduces the size of the model. Where if for instance, like the example I gave earlier, if you're saving that, serializing it and then shipping it off, you might want to kind of a priori trim those vectors before you ship it off to the servers to actually do the kind of recommendations. So this is the part where we're actually kind of doing the recommendation and then like kind of doing the retraining. So you saw, I had my choices and then I had that vector of choices I made. This most similar cosine is basically doing the cosine similarity between the word or the words in question and all the other terms. So this would be products, for example, but it could really be anything. And returning kind of a stacked list. And so that's this. Where I'm kind of producing these, and I do a little bit, so you can serialize it, so you can move it across the wire. But that's what these are doing, and I'm retraining it, so you can kind of imagine as you get more and more information, you're just basically sending documents into this training, and you're getting better updates. And then there's, similarly, there's the transformation side of this, where you're and so this was those 10. That's what I kind of showed earlier, where I'm getting the term, and then I'm kind of producing the result vector and then returning it back. So this is this is the just kind of like diagnostics, or like if I have this term, what does it look like? So in terms of similarity methods, there are a lot that are available. So there's most similar. Cosine, there's then most similar, there's insimilarity, and there's doesn't match, which I think is kind of cool. I don't know if you ever played the game when you were, like 6 years old or whatever, where you had like a cucumber and then a banana and then an apple and then an orange, and it's like, well, which one of those is least similar or doesn't match the rest? I was probably jaded as a child, so that's kind of Word2Vec, and it tends to work pretty well. One kind of quick thing. This is a maybe. So Word2Vec can be really useful, but you end up getting these vectors on a term basis. This can be a little challenging if you're trying to do like aggregations, or say I'm so kind of the fundamental kind of the way we've kind of been viewing this problem is a person as a document. The products they purchase are terms. So you get the terms for the products they purchase. However, you might want to say, okay, how similar is Trent to this other customer? So that's probably a really natural next question to ask. Or if you're doing some sort of clustering and you want to say, I have these 10 emails to send. Let me kind of cluster them into groups. If you're only kind of using these term vectors, one problem that arises pretty quick is the natural idea might be, I want to then average these terms. The problem is if I have these various products kind of represented in space, I just realized I look like the flailing arm guy. So if you have these products like represented in space and then you average them together, you kind of drown out a lot of information. So this is where Doc2Vec may be kind of more appropriate for some of these terms, is it kind of it's looking at the document itself and trying to produce a vector representation of that document, not the individual terms. So it allows you to kind of move up a layer of abstraction, which might be more useful. It also has a kind of similarity functions, which you can use. So in case B, so that was kind of like a recommendation system, and that was like, oh, we have these NLP-focused algorithms. How do we kind of slant them into maybe other applications? Then another one, another kind of interesting idea, or maybe kind of more, it's closer to NLP is actually doing text analytics. So like I mentioned earlier, I looked at the inaugural addresses over time. Don't try to like derive any meaning from this. This is just kind of showing what you could do. So I have basically the years running across the y-axis from 1789 to 2009, and then I chose 25 topics. So if you really wanted to dive into this, you can kind of look at the topic trends over time. And you might want to look and say, maybe kind of in the early days we were more focused on being a union, and then as we kind of transitioned into the kind of mid 1800s, late 1800s, maybe it's more kind of industrial revolution focused, things like that. And then as we kind of move later on, you get some more topics and some kind of changes. So you kind of do some interesting trends over time. There's a paper around modeling scientific topics over time, which I think is a really good paper, and it kind of talks about the power, or at least shows in a really good manner the power of NLP for kind of trend analysis and things like that, and why LDA is a really good choice there due to its interpretability. So let's talk about this kind of analysis real quick. I think probably only have a couple minutes left. So this is the kind of the corpus you saw earlier, except it's changed in a little bit. So there's this yield key. So kind of what I found is when working with Gensim is you want to have kind of one way to produce the training examples and one way to actually produce the scoring examples. So the reason I have this yield keys here is I'm yielding, if I want, what I can do here is just yield the bag of words to actually do the training. But when I'm doing the scoring later, I want to be able to associate some document or some document ID with the score or with the outcome. So that's what that's doing. Is I'm just saying, okay, when I do this first, I don't want those keys, and I just want to do the training. And when I'm doing the actual analysis, I want to be able to associate an ID there. So that's what I just said there. That's what I just said there. So then we have, so this is kind of the data, like I guess I would call it the data generation process, or kind of like the scoring of the underlying models. So I'm just creating, kind of iAddress, which is the inaugural addresses, LDA with like that corpus passed in, the number of topics, 25, how many passes I want to do. This is basically, you want to train more so you can get convergence depending on how big your underlying data set is. And then this ID to word is kind of allows Gensim to translate between tokens and words. So then you can actually do like the data analysis on it, where you might basically iterate through all of the documents and create this data frame where you have the president, the kind of fundamental like topic to probability vectors, and the year in question, and then you would potentially do some plotting or something like that to kind of produce something that looks like this. So real quick, the kind of takeaways. So hopefully you got enough, of an introduction to NLP to be quote unquote dangerous. So NLP transformations have different strengths. There's the querying side, which I talked about with kind of the word to vec example. There's the LDA, which is a little bit more probabilistic focus, which might be nice for kind of analysis and interpreting results. And then in terms of Gensim, we kind of talked about there's this pre-processing step where you have your document, you need to turn it into words or turn it into something that's useful for later. And then there's the kind of the model transformation step where after you have that vector representation of your underlying documents, then you score them and then you use them further. And then there's this kind of querying analysis, two sides to NLP kind of focused on what you want. So I think I'm not real good on my time. So I'm hoping happy to answer questions, or if you want to come up, that works too. Okay, cool. Thanks.